semester BTech students, both for CSE and ECE stream. And today we shall learn about the inner product space or Euclidean space. This is from module 3 of your syllabus. So let us now start. To learn about Euclidean space or linear space, that is to introduce the inner product space, first and foremost we have to be acquainted with what basically inner product is. Indeed, we are litigating with a real vector space. So we shall mainly be concentrated upon real inner product. So let us now see how does it look like. Here we have considered a vector space V over the field of all real numbers. That is the real vector space. And we are considering a function f whose domain is the Cartesian product of this vector space V cross V, and the codomain set is the set of all real numbers. That means we have considered a function from the Cartesian product V cross V onto the set of all real numbers. If this function satisfies these four consecutive properties 1, 2, 3 and 4. Number 1 is a symmetry property, number 2 is a linearity property, number 3 is homogeneity property, and number 4 is positivity property. Then this function will be termed as a inner product. So what are these properties? Let us now see one by one. First, symmetry. That means the domain of definition of the function f is the Cartesian product set V cross V. So each and every member of this domain set will be of such type alpha comma beta, that means having two components, each member being from this vector space V. The symmetry property tells us if we change the order of these ordered pair, if we change the order of the components of this ordered pair element, the functional value will be remained same. That means the functional value of alpha beta under the function f and the functional value of this point member beta alpha under this function f will be same or equal real number. This is called the symmetry property. Number 2 is the linearity property. Linearity, for this linearity property, here we have considered a member or element from the domain of definition alpha comma beta plus gamma, alpha comma beta plus gamma. First component is a single vector alpha and the second component is the addition or composition of the vectors beta and gamma. I do think you all know how to compose two vectors from a vector space. This is the component wise addition. So if we consider this element alpha comma beta plus gamma, obviously under this function f, this will be converted into a real number. And if we individually consider these 2 points alpha comma beta and alpha comma gamma separately and calculate the value of this point alpha beta under this function a and the value of this point alpha gamma under this function a, this will be 2 real numbers, and if we add these 2 real numbers, this will be equal to the real number which has been obtained for this point alpha comma beta plus gamma. This is termed as the linearity property. The third one is homogeneity property. Here we have considered a point alpha comma beta from the domain of definition of this function a, and merely we have multiplied each and every component. That means once with alpha we have multiplied by an arbitrary real number c and consider this point c alpha comma beta, and we have also considered a point alpha comma c beta. Here we have multiplied this real number c, arbitrary real constant c, with this vector beta, the second component element of alpha beta. The functional value of this point c alpha comma beta and alpha comma c beta are same. And if we consider the functional value of this point alpha comma beta and if we multiply that functional value, that means that very real number, by this real constant C, this value will also be equal to these two equal real numbers. That means the functional value of this point C alpha comma beta, alpha comma C beta, and the C multiplied of the functional value of the point alpha beta are equal. This property is termed as homogeneity property. And the fourth property is very important. This is the positivity. So let us now see how does it mean, what does it mean. Here we have considered a single point alpha from this vector space V, and just we have ordered pair, that means alpha comma alpha. Obviously this is a point of this domain of definition of the function A, and the positivity condition tells us that the functional value of this point alpha comma alpha will be a positive real number, and obviously alpha is not a null vector theta. If alpha be a null vector theta, then that functional value will be 0. And if these four conditions are consecutively satisfied for such type of a function, then that function or this very function here f will be termed as a inner product. Any vector space here, as we consider V, equipped with such type of inner product will be uttered as a Euclidean space or a inner product space. Okay. In our next class, we shall illustrate this definition through an example.